Good afternoon. Now we will start the second session on statistical physics. The speaker now is Professor Fábio Araão from Universidade Federal Fluminense. Please.
Thanks, Ismael. Well, thank you, everybody. Thanks, everybody, for coming. Hope you enjoyed this section, this presentation, and I also thank very much the organization for inviting me to be here in this workshop. And well, I speak about simulation of nanostructures or materials growth to relate the microscopic dynamics of these growing systems and the resulting morphologies. To a large extent, this is a continuation of the talk of Ismael in the morning, in which he spoke about kinetic Monte Carlo simulations. So I will not give details on kinetic Monte Carlo simulations here, but all the results that I showed to you are obtained with that method. Then, first I will try to summarize what are the main aims of our research. Is to develop statistical mechanics models far from equilibrium, far from the thermodynamic equilibrium, to relate these two things, the microscopic dynamics of growth or of dissolution. Ismael gave you some examples of dissolving materials like calcite. Relate these dynamics with the morphology of these materials, like thin films and other nanostructures. So we focus on processes occurring on surfaces like the deposition of atoms or molecules, their adsorption, possibly their dissociation, like this molecule, which is dissociated in two atoms, the surface diffusion, which is the random motion of atoms or molecules on surfaces, and reactions that may occur between those adsorbed molecules, possibly the desorption of some molecules. So all these processes appear in the simulations that we have been doing to describe these growth processes, which are experimentally done by several different techniques. And now I will discuss some applications of our work, separating them by the experimental method used to produce these nanostructures, because each experimental technique has some peculiarities that have to be properly described by our models. Then, what is in common in all these methods? The one thing that is common among all these methods is that the rates of microscopic processes, like those processes I listed to you, they are written in terms as an Arrhenius factor, or one constant multiplying a Boltzmann factor, in which here we have a rate constant. This rate constant may be number of attempts per second, or number of hops per second, or in some cases, some rate like the number of moles per square meter per second, and then an activation energy at microscopic level. Usually it means an energy barrier that has to be overcome by an atom or a molecule to change its state, to change its position, or to undertake a reaction. And then KBT involving the local temperature. An assumption underlying all these methods is that the atom or molecule or nanoparticle, which is the building block of our model, it is in thermal equilibrium with the neighborhood, with a nanoscopic neighborhood. But the whole system is continuously being brought far from equilibrium due to other processes. for instance, due to the deposition of material, which is the max flux from vapor of solution, or due to the presence of reactants in solution that lead to irreversible reactions. So these are mechanisms that bring the physical system far from the equilibrium conditions, far from thermodynamic equilibrium conditions, while these microscopic processes, they tend to bring the system to an equilibrium configuration, but usually they act in small sizes at small scales. So frequently what we get in modeling systems with kinetic Monte Carlo simulations and with this type of approach is local configuration that represents some type of equilibrium, local equilibrium, but a global configuration that is representative of the far from equilibrium conditions in which the material is grown. So the first application I show to you is the initial growth of heteroepitaxial films. This is a subject that is still under development in our group. We have a collaboration with a group from the University of Tübingen. There are 2 students from there here in this talk. And so this was I will summarize here the first work we did along this line of studying initial growth of heteroepitaxial films, which means film grown on a surface, on a substrate of a different material. Then, for this purpose, we used a Clark-Vedensky type model in a simple cubic lattice, like this one, showing the organization of some atoms or molecules in a mound, where we have some atomic or molecule flux. So here a collimated flux of molecules, and surface diffusion with a step edge barrier and a higher diffusion coefficient on the substrate. Due to the much higher diffusion coefficient of the atoms on the substrate, then it facilitates the formation of islands. When they aggregate at an island, when they jump to the second layer, their mobility is lower. So this facilitates the formation of these islands. Then, for several processes illustrated here, I show the rates of these processes and the corresponding probability for the process to be executed if the atom is going to change the height of its position, if it is going to another layer, if there is a change of the layer. For instance, in this case, this blue atom is going to move to the top of this neighboring column. So it has to overcome a barrier of height 2. So due to the hop, no, not only 2, 1, 2, 3. The difference of heights is 3. So the probability of the hop is given by this quantity, and the rate of the hop for this atom compared to the other atoms has this form: dA, a coefficient dA, multiplied by epsilon 4. This factor epsilon accounts for the number of nearest neighbors, which is 4 for that atom. So this is the way in which we define the different rates for the movement of atoms or molecules in this deposit. And we measure quantities like the local roughness. Local roughness is measured in small windows gliding along the surface. The roughness is simply defined as the standard deviation of the thickness inside that window. The global roughness is equivalent to the local roughness in a very large box along the whole system. It is also the standard deviation of the thickness, and the autocorrelation function measures the correlation of heights in different points, the fluctuations relatively to the average in different points. In this work, published in 2021 and in a sequential work in 2022, we showed some simulations with negligible barriers at step edges, with the formation of large islands on the substrate, and then the coalescence, and after the coalescence, a very small roughness, a growth of the film nearly layer by layer, and the evolution of the roughness is in this plot, the green line, illustrated by the green line, so that while the islands are growing separately, there is an increase of the roughness, and then the roughness reaches a maximum near the point where the islands coalesce, and then it drops. And this was observed in hot wall deposition of cadmium telluride on polymeric substrate. Here are the results of the initial growth, and at between 7.5 and 9 minutes of deposition, we see that the islands coalesce. There is evidence that the islands coalesce in this region, which is exactly the point in which they see the maximum of the roughness. This was the first application we found for illustrating this general feature of the roughness passing through a maximum, and there are also other clear applications of this type of approach now with the organic films. And from this study, we could get a rough estimate of the diffusion coefficient of the molecules, of the cadmium telluride molecules on that substrate at the growth temperature. Usually, from these approaches, one thing that we can usually measure is the diffusion coefficient of atoms or molecules on the relevant experimental conditions. Then we also made simulations with large barriers at step edges, and in this case, we also see the formation of large islands in the beginning of the process, their coalescence, but in the coalescence, we only see a plateau in the roughness, and after that, the roughness continues to increase because there is formation of mounds. We are currently improving models of mound coarsening, improved compared to these works. For instance, one recent publication is in PRE of last year, and we are finishing the preparation of a preprint in which we improve these models of mound growth, which are also frequently observed in experiments. Then I will go to another application, which is the silver electrodeposition. I will not only speak about silver electrodeposition, but also electrodeposition of other materials. This work on silver electrodeposition was done with colleagues from France. One colleague from Sorbonne did the electrodeposition of silver on a substrate patterned with gold nanoparticles with average diameter of 4 nanometers, very small gold nanoparticles. They allow the nucleation of the silver electrodeposits, the silver deposit, at several points of the substrate. Then, after roughly 1 hour of electrodeposition, what they observe with the microscopy is that some microparticles of silver were formed, these one-faceted nanoparticles, typically with a size of 1 micrometer. The faces have typical widths of 1 micrometer, and at the late stages of the electrodeposition, from the edges of the microparticles and from the corners of the microparticles, some branched structures appear, some dendrites with the shape of pine trees, like this one. This one is also highlighted here. Sorry, they have the shape of pine trees. And then we've developed an electrodeposition model for this type of process. The first publication of this electrodeposition model was in Journal of Physical Chemistry C, 2018, not with the application to silver. And then in 2022, the work concerned with the silver electrodeposition. Then what are the conditions of the model? We consider that there is a solution above the cathode and the diffusive cation flux. When the cation flux, when the cation reaches the surface of the deposit or the electrode, it undergoes a fast electrochemical reaction. It immediately reduced to a silver atom, and then this silver atom can execute diffusion limited to a certain time interval. Well, what's the reasoning to use a model like this? The reasoning for this is when a dendrite of silver is formed, it's crystalline. The dendrite is crystalline. The tip of the dendrite is crystalline. But the electrodeposition takes place in a layer which is amorphous surrounding this crystal. This is amorphous. This layer is amorphous. It has widths typically of 5 nanometers. And then when we describe surface diffusion for the reduced atoms, what we are describing is the mobility of the atoms in this amorphous layer until they crystallize, until they attach to the growing crystal and become part of the growing crystal, expanding the growing crystal, the core crystal. And then what we are describing with surface diffusion in this model is the mobility of the silver atoms or nanoclusters, nanoaggregates of silver in this amorphous layer surrounding the dendrite tips. This is based on a work not of my colleagues from France, but on images that several different groups took on dendrites of silver and also of other materials previous to our works. In the last 20 years, there are some works along those lines. And then what we obtain with our model, as I told you, these atoms execute, the cations execute a random motion, then they are reduced, and then the atoms can move to at a certain time interval. Then, if we produce a pattern of nanoparticles, put a pattern of nanoparticles on a surface, and then the deposition begins. In the beginning of the deposition, there is formation of some pyramidal particles on the nanoparticles, which are representing the gold nanoparticles. So this would be the growth of the silver, also at nanoscale. If we let the electrodeposition continues, then we observe the formation of the pine trees on the whole substrate, in this case. But then we were working at nanoscale. We cannot go to the microscale in the simulations. We do not have computers for that. Then the next step was to see what happens if we begin with a faceted particle and try to make the electrode deposition here, assuming that due to some other mechanism, the initial faceted nanoparticle appeared there. Then, during the electrode deposition, then we observe the formation of the pine trees, preferentially at the corners, and some of them at the edges of this particle, exactly as observed in the experiments. Then we move it forward and try the electrode deposition on very large surfaces. During the electrode deposition, very large surfaces, we observe for sufficiently high mobility of nanoparticles, also the growth of the nanotrees parallel to each other, but in this case, the growth is allowed at all points of the substrate. And I think, I didn't put all the images I have here. We also made some tests with high mobility of the particles on a surface and putting a single seed. And putting a single seed on a surface, we get larger pyramidal particles, much larger than this one shown here. And after the formation of the pyramidal particles, there is branching, so the pine trees begin to form too. So from this study, we could estimate the parameters of the model suitable for the silver electrode deposition are these values, and they lead to this diffusion coefficient of the silver atoms before the crystallization in a process like this. So this model is able to give an idea of the diffusion coefficient of silver atoms in those amorphous layer before their full crystallization. Next, I show to you results of more recent work done with the group of André Paza, who is here, who performed the electrode deposition work of iron on silicon. One interesting thing is that they observe, well, they grow compact films of iron on silicon in the electrode deposition conditions that they use. The films are compact, but they observe the secondary nucleation of iron grains after some thickness was grown. So, for instance, here, these images could identify the grains with different orientations, and here we see two grains with this orientation 211 that do not have contact with the substrate. So they only appeared after the growth of 50 nanometers of the film on the substrate, or 150 nanometers from the substrate. So they are not grains formed on the cathode. They are secondary grains. And then we try to model this with a similar approach to that previous one. The main difference of the model is that in the beginning of the process, we assume that the reduction rate is much smaller on silicon than on the iron film. This facilitates the formation of islands because iron is a metal, silicon is semiconductor, so we assume that there will be a larger electron density on the iron deposit, and this leads to initial growth of islands, and after some time of deposition, we see a landscape like this with the identification of the different grains. Our model did not incorporate the secondary nucleation, but it has several features in common with the experimental deposition, which are, here is the roughness as a function of time, and here is the correlation length, the lateral correlation length as a function not of time, but of the thickness of the film. Then the roughness increases, has a plateau, and then it begins to rapidly increases at thicknesses larger than 100 nanometers. And the correlation length increases, then has a strong drop at some point, which is identified as the thickness, nearly the thickness in which the secondary nucleation appears, and then it grows again. What we see in our simulation is that the roughness has a similar feature, so that it increases, then has a plateau, possibly a slight minimum, and then it rapidly increases, suggesting here that some instability is developing. The instability may be a mound growth, may be dendritic growth, and then we see this rapid increase like in the experiment. The correlation length may have a small decrease, but not as large as that observed in the experiments. So we associate, so this is another reason for us to associate this large decrease with the secondary nucleation, which forms smaller grains, and forming smaller grains, then the lateral sizes of correlated regions become smaller. But the global roughness is almost the same as in our previous model. Then, going on, trying to be faster now. We also improved the electrode deposition model in a recent work in 2022. This was done with Ismael and with a colleague from São João del Rei. And well, I will skip this point because the main aim of this improvement is to use parameters for the simulations, G and P, which are really temperature-like parameters, so that terraces become smoother, branches become thicker when one or both of these parameters increase. And here I show to you another application, another recent application of our work. It was for the growth of silicon films with tantalum nanoparticle scaffolds. So this is a scheme of the deposition. This group in 2017 performed this work to produce anodes for lithium batteries based on silicon, but nanostructured silicon, so that it could have improved properties as anodes. They used silicon to tantalum ratio of 97 per 3 in number of atoms. So they deposit a thin layer of tantalum nanoparticles. The average size of the tantalum nanoparticles is 3 nanometers. And then they deposit a thick layer of silicon, roughly 30 nanometers, then another thin layer of tantalum nanoparticles, and so on. And with scanning electron microscopy, what they see is the initial formation of shells around the nanoparticles by the silicon. This is one scaffold, one full layer of tantalum nanoparticles, and nominal 3 nanometers of silicon. So the silicon surrounds those nanoparticles. When when 15 nanometers of silicon were deposited, then this is the shape that they observe. This is the image that they obtain with the SEM. And then the hybrid films, they are rougher than the pure silicon films. If only silicon was deposited, it has a very smooth surface, and the porosity of the hybrid films is nearly 20%, while the deposition of only silicon led to a very low porosity. Well, silicon was deposited by sputtering, in this case, and the tantalum nanoparticles by evaporation. And then here is the model we developed. Here is the tantalum nanoparticle, much larger than one silicon atom. The model is also done, is also simulated in a simple cubic lattice. So the tantalum nanoparticle is a discretized sphere. The aggregation of the tantalum nanoparticles is at the first contact because they are thermally evaporated. So when they reach the substrate or another particle, they immediately aggregate at that point. But that's not the case of the silicon, because the silicon is being sputtered. So there is a bombardment by argon ions in ejection of atoms that rapidly move to the substrate. Then they reach the substrate with large energy. It's not a thermal energy. Since they reach there with a large energy, then there will be a stage of thermalization. During this stage of thermalization, the atom can move up to a certain distance until it thermalizes to the room temperature, because the deposition was performed at room temperature. So during this process, what is going to happen is that the atom can move to nearest neighbors or next nearest neighbors with some probabilities for these hops. And these probabilities of hops depends on the local neighborhoods. The larger the number of neighbors, the lower the probability of executing a hop. So this is an illustration of the different hops at different points. And then what we obtain after depositing one nanoparticle scaffold and one silicon layer. This is a top view. This is the cross-sectional view. So you see here these gray nanoparticles. They form the scaffold, and then the silicon deposits first around the nanoparticles, and then they form these cones. And these cones leave some gaps between them. They go leaving these gaps. These gaps are responsible for that 20% of porosity. And here is what we obtain after 5 nanoparticle scaffolds and 5 silicon layers. So here the nanoparticles are very small, but there is one scaffold here, one group of nanoparticles here, another group here, another group here, then the fourth one, then the fifth one, and from each of these groups of nanoparticles, these cones of silicon, they grow with increasing width as the height increases, but the width grows slower than the height. And then there is formation of some pores between these blocks of silicon. So the structure is completely, the pores are connected from the top to the bottom in this system. Like what is observed in the experiment. There is conductivity until the from the top, where there is an electrolyte to the when they use as an anode, they put an electrolyte, and then there is conductivity of the electrolyte that fills the pores. Then, well, this ends my talk. And how many minutes? 5 minutes? Okay. Then, my current research team is this one. At UFF, a visiting professor, Fernando Oliveira, who is now visiting UNB. Next week, I don't know where he's going to visit. Yes, you are specialized in being a visiting professor. Okay. And 2 postdocs, Edwin, Nathan, who spoke to you in the morning with FAPES grant. Currently, 3 students, Andres, who is in the PhD. He was the one who did the simulations of sputtering that I showed you now, of the hybrid films. And Fabiana and Mariana, they are taking the master in the biosystem engineering course. Their works are on environmental education programs, and 3 undergraduate students working along similar lines, and current collaborators, frequent collaborators from other institutions are Ismael, who is here organizing this meeting, Sidney, who performed some of the simulations of electrodeposition, and Thiago Assis from Salvador, who is also involved with some models of film growth with me. And collaborators from other countries, from Brazil. The only one here in the list is André Paza, who is here collaborating with us on electrodeposition works, and the 2 guys from France that who also work on electrodeposition modeling, 2 in Lyon on different subjects. The group of Tübingen working with modeling of organic films, and Sue Brantley from Penn State, I work with her on geochemistry, and Vaughan, I work with him with diffusion in disordered media. Then, the financial support to our work is listed here. These are the current projects. At that time, I think I didn't include an international cooperation project of CNPq, which was approved at the end of last year, and in which Ismael, for instance, participates, and will take a grant in 2026 for spending 1 year in the US for a postdoc. I hope it works. And here a list of the funding agencies until now. And to end, just a brief mention that besides these works I am on applied physics, I'm also involved in a work of the project, a big project of the call Amazonia Plus 10, which was released in 2022, is a cooperation work between institutions of different states, one of them in the Amazon, which is the state of Amapá. There are 2 institutions there in Amapá, the Embrapa of Amapá and the university, the Federal University of Amapá, involved in this project, also the funding agency of Amapá, besides the funding agencies of São Paulo and Rio de Janeiro. Most of the support was provided for the Rio de Janeiro group. There I am the head of this project. The main aim of the project is to produce energy from biomass in an island near Macapá, and where they produce much açaí, and then from the residues of the açaí, the core of the açaí, for instance, they can smash it and produce gas, produce fuel gas from that, and this will help the sustainable beneficiation of the açaí, the industrialization of the açaí in a sustainable way in that community. That's the main aim of that project, and also to integrate this energy source with the photovoltaic source that they already have in the island. And what's my part in this work is, sorry, this is written in Portuguese, but most people will understand. I am responsible for a program of environmental education and scientific education in that island. I've been there for 7 days for a work meeting with teachers of the school of that island, and another teacher for another school. He is also a community leader at uh, at another island of the region, and he's interested in taking the master course there with me, possibly from the middle of this year, and also bringing this project to improve scientific teaching at other communities, at schools of other communities at that region. So, and that's a project in which the next year I hope I can engage other university professors interested in these problems, interested in participating in this type of project. Then, to conclude, students and postdocs are highly welcome in our group, in our research group, multi-institutional research group. As I could show to you, there are people from several different institutions involved with us, and also collaborations with experimentalists are also highly welcome. This is a list of recent publications related to this work, and I thank you again for coming. Thank you for your attention. I don't know if I will have time to answer questions, but I will be here until tomorrow in the dinner today. So thank you very much again.
Hello. Okay, thank you, Fabio, for the talk. We started 10 minutes later, so we still have questions for time for a single question. So let us thank again the Professor Fabio for
Thanks.
the talk. Now we have the talk from Professor Fernando Oliveira. If I'm not mistaken. É o Fernando? É o Marcelo? Será que eu confundi? Okay. Sorry, it is Professor Marciano. I exchanged the. I looked back. I didn't see him, so I probably Fernando then. So. Okay. So. Pode pôr aqui. Tem uniforme da conferência? Fernando tem que uniformizar.
Alô? Yeah. Se você quiser, eu conto. Seja. Ok.
So,
Deixa
eu te falar uma pergunta.
alô? Tá baixo? O que você acha? Alô? É que eu esqueci de ligar, né? Pois é, aí era que tava baixo. Não, eu esqueci. O dele que ficou alto, acho que do microfone agora. Mas acho que agora tá bom. Do jeito. Ô, Tarcísio, faz um teste no seu microfone. Calma, tá bom? Quanto perto do amigo de fazer prova? Mas tem que ser uma que pode passar na televisão, viu? Antes das 10. Nada de urso, viu? Mas eu acho que você falou lá do verso, acho que vale a pena. Mas vou ver se eu converso com o menino da Alemanha hoje, tá? E aí é mais. Sim, o Chico cedo, por favor. E aí a gente pode conversar. Porque realmente não tem mais de manhã, tá bom. Eu vou falar. Eu acabei de ter o Alexandre, pô, dá pra confiar mesmo? Eu não sei. Não, mas é de baixo, eu vou fazer.
Alô? Ops. Regula, volume regula aqui? Alô, 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 alô. Alô, 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 alô. Ah, tá. Alô, perfeito. Ah, hello. Ok. Já tá, botei no máximo aqui, beleza.
So now we are going to have the talk from Professor Tarcísio.
Okay, thank you for to the organization for inviting me to present this talk here today, and to everyone that is here also. Well, I will talk about systems with long-range interactions. I will explain what they have of special compared to what we call short-range interactions, which is the kind of system we usually study in statistical mechanics lectures. And I will show you some interesting effect we discovered some time ago about Goldstone modes in such systems. Goldstone modes are best known for the role they play in the Higgs mechanism that gives mass to particles. Then the Goldstone mode is related to the Higgs particle. But we can have also the same kind of phenomenon in classical systems, like in soft mode turbulence in liquids is a very known example. And I will show what happens in some interesting phenomena that occur in systems that have what we call a long-range interaction. The most obvious example of long-range interactions are gravitational force and Coulomb electric force, where I show you a few other examples. This work in Goldstone mode was done in collaboration with Bruno Marcos from the Université Côte d'Azur in Nice, France, and was published in this paper here. But I will also discuss a little bit of what we did in our group, mainly with a friend Hannibal here and Markamati and other people, the students of our group. Well, the first thing is then to define what I call a long-range interaction. Is essentially an interaction that for long distances it decays as a power law, where the exponent of the power law is smaller than the distance, the dimensions, sorry, of your space. Then what happens then is if you compute the potential energy, this interaction potential, if you compute the potential energy inside a given sphere of radius r, you see that if this exponent is smaller than the spatial dimension, your potential energy diverges with the distance. So we have the effect of very far particles can be even more important than near particles. The most self-evident example is the gravitational force in among galaxies, globular clusters, or inside a given galaxy. Okay, where your interaction potential decays like 1/r. That means the exponent is 1, which is smaller than 3, which is the spatial dimension. But there are other examples like two-dimensional flows, like here in the surface of Jupiter, we have this turbulent flows that creates those structures like the red spot, but there are many other spots like this. And there are some models that consider these spots interact and these vortices interacting with a given potential, which is also long range. other model, of course, charged plasmas with particle interactions in plasmas is another example. Some spin models, and classical and quantum also. I will present a few here. 2D gravity is a simplified model of gravity, and self-gravitating sheets is a one-dimensional gravity. And, of course, small systems, which are a special case where, of course, the range of the interaction is of the size of the system. In what did they have, what is different about these systems? They can, not necessarily always, but they can present some interesting properties. For instance, they are non-additive, particularly in the energy. If I take a galaxy, divide it in two parts, the total energy is not the sum of the two parts, because the interaction energy among these two parts is as significant as the energy, the potential energy inside just one of each those parts. So the energy is non-additive, and this creates another little problem, is that if your energy is non-additive, your entropy will still not be neither additive. And this can generate a whole debate, but we will not discuss this here. But in particular, we can have a negative heat capacity. And this does not violate the second law of thermodynamics. Thermodynamics is always valid here. But how can I have a negative heat capacity? Well, a very simple example. I will show something more interesting. But if you take a satellite orbiting the Earth, if you give some energy to the satellite, he will go to an upper orbit, but the kinetic energy is smaller. Okay? So if you take a gravitational system, like a globular cluster, and you play God and you give energy to the stars in this globular cluster, it will go in another state where the average kinetic energy is smaller. This is what it means, a negative heat capacity in this case. But it doesn't happen always in plasmas. The heat capacity is always positive. This happens in attractive systems. And they also have a very special dynamics when evolving to equilibrium. The time to reach equilibrium, which is really short in usual systems, is very long in those systems. They diverge with the number of particles, in fact. If you take, for instance, a globular cluster, which has typically 10,000 stars, something like that, this order of magnitude, a globular cluster, the velocity distribution is very near a Gaussian, okay, because it's already thermalized. But if you take a galaxy, 1 billion, 10 billion stars, the velocity of the star is not a Gaussian, because the time for this velocity to thermalize is much, much bigger. I will show some examples in a moment. And we can have some anomalous diffusion, non-ergodicity. There is a lot of interesting things that happen in these systems that were studied in the literature. I would study some simplified models here to present this. Well, the ring model is very simple. You take a circle with a given radius, and you put particles in the circle that are constrained to stay in the circle, and the interaction is a gravitational interaction. Attractive, you can put it repulsive if you want to. Then the potential is proportional to 1 over the distance. As a gravitational potential, is just a matter of geometry. And well, we choose the units so we can have this Hamiltonian. There are 2 details I will explain here. First is we sum a small number, an epsilon, which we call a softening parameter. This is very common in some computer simulation of gravitational systems to avoid the divergence of the force at at 0 distance, which is very cumbersome in a computer simulation. So we just add a small epsilon here. And there is this factor, 1 over n here. The reason we put it, well, you can do it by a simple change of time units, which is well-defined, provided the number of particles is finite. Then we can insert this 1 over n term here. The advantage of doing this is because here we have n terms, the kinetic energy scales with n. But the potential energy is proportional to the number of pairs of particles, and it scales roughly like n square. So if we put this 1 over n factor here, this potential energy term scales with n. That makes the energy is non-additive, but it is extensive, which is it can help us a lot in here. And well, it's just a change of time units, provided you don't go to the thermodynamic limit and make n infinity. Okay. Then we have also what we call the Hamiltonian mean field model that I will study with more detail in this talk. It just is just a limit of this ring model. We can take a Fourier expansion of the potential and retain only the first term. Or we can think as making this small softening parameter, make it become big. It's just a toy model anyway that has this special form here. And we can define, we can think it's as classical spins, rotors, each one with a coordinate theta and angular momentum p. And we also define the magnetization in analogy for a spin system, which has two components. That is magnetization is essentially the average of the cosinus and the sinus of the angle of each rotator or each particle. This model, it can be, it's solvable in the sense that I can compute the equilibrium property exactly. I can compute the partition function, and I can write down the equilibrium distribution function, which is given by this expression in terms of m, the total magnetization, which is a solution of this transcendental equation with I1 and I0, the special Bessel function of index 1 and index 0. Beta is 1 over kt, the Boltzmann factor. And this is the equilibrium distribution. And also this model is very useful because the simulations, we can make it scale, the time of computation scale linearly with n. Opposite to other systems, if I do this for a normal gravitational system, for each particle I have to compute n forces. Then this makes a computational effort that scales with n square. But here I can compute the force, simply computing the average magnetization. The forces have this very simple expression, and then I can do computer simulations very easily that scale with n. So here, well, can do like a million. My personal record on my computer at home is 100 million, and in a feasible time. There's also what we call the 1D self-gravitating particles. These are particles. This is a solution. Essentially, it's a solution of the Poisson equation in one dimension that gives us this potential, just the absolute value of the distance. It's like infinite sheets of matter with a constant density that interact with each other and can cross each other. We can also have two-dimensional self-gravitating particles. Well, for instance, if you take a galaxy, that all the stars live precisely on a plane, on the plane of the galaxy, you can model this with this kind of model. And this, again, this potential is the solution of the Poisson equation in 2 dimensions. Then, as I told you, the systems have different evolution stages, and it takes a very long time to evolve up to the thermodynamic equilibrium. This is a very simple example for the HMF model, the Hamiltonian mean field model. This one here, which is very easy to simulate. And this with 10,240 particles with a time interval in the, I did a symplectic integrator here. Then we have to simulate up to 10 to the power of 7 to reach equilibrium. How I know that I reach equilibrium? Here is the plot of the 4th and 6th momentum, reduced momentums of the velocity. That means I take the velocity and divide by its standard deviation, essentially, and then do the average. And for any Gaussian distribution, the values of the fourth and sixth order momentum is 3 and 15, which are shown here. Then we can follow the evolution towards equilibrium more easily in this graph. First, the system goes to some kind of what we call a quasi-stationary state, which is non-Gaussian, but he stays, nevertheless, a very long time here. And this quasi... Hello?
Hello?
Okay.
Maybe you can use the microphone because it's probably the battery is probably dead.
Hello? The first stage is what we call a violent relaxation that occurs in a very short time. There are some theories to describe that. Then, after the violent relaxation, the system stays for a very long time in this almost stationary state, a quasi-stationary state. And then it slowly relaxes to equilibrium, like here. But the point is, if we raise the value of n, the time to reach equilibrium is it diverges. Here, it took a time of 10 to the 7 for just 10,000 particles. Now, we can show that, in fact, this evolution towards equilibrium is due to collisions among the particles, and the effect of collisions, we can show, it vanishes when you make n go to infinity. So we have a very different type of dynamics compared to short range when your system very rapidly reaches equilibrium. Okay. Well, we can describe this evolution toward equilibrium. We'll not spend too much time using kinetic theory, using kinetic equations a la Boltzmann. But for short times, the system, it can be shown for very large n. The system is well described by the Vlasov equation, which is a mean field equation. And the Vlasov equation is the equation which describes this initial state of the violent relaxation towards this quasi-stationary state. And with we can correct the Vlasov equation with collisional terms. That gives us either the Landau equation, which is for a perturbation approach, or the more precise Balès-Coulenard equation, which is very used in plasmas. Then describe the evolution to equilibrium. Okay, so this is how we did some works in there are some of our papers here. Aníbal also worked with me a lot on this. This is just, I will show you the Vlasov equation, which describes this initial evolution. I did here is a very simple mean field equation, which simply says that the one particle distribution function, which is represented here for the density of probability of one particle having momentum p, position r at time t, satisfies Liouville theorem for the one particle state space. Then its total derivative is 0, which is given by that. F is a mean field equation, which is minus the gradient of the mean field potential. The mean field potential is simply the average of the interparticle potential done using the one particle distribution function. Then is a nonlinear integral differential equation, which is, of course, very complicated to solve, even numerically. We can try to obtain some particular analytical solutions. I've been working on that with my colleague in Marseille, Yves Scans, but for simple models, of course. But here we can solve it numerically, at least for in one dimension. This is for the same model, the Hamiltonian mean field model. This initial condition is what we call a water bag initial condition. Here we have on the horizontal axis is the theta variable, in the vertical axis the momentum variable, and the distribution function is 0 except in the black region, which is, it has some value, it's constant value, which is normalized. And we solve this on the computer. This one was done in a GPU, graphic processing unit, to accelerate. So there is, since the one particle distribution function satisfies Liouville theorem, the area of the figure must always be the same. The volume in phase space, in this case, the area is conserved, and we have some filamentation process, and the tendency is to, here there is an average, and there is a tendency to form what we call this core halo structure in the phase space. Well, so, but I will jump this part of the caloric curve, so, and we'll discuss now what happens, where is the Goldstone mode in this model and other models, and what happens if interaction is long range. Oops. Well, the first thing is when I have a periodic coordinate, like in the HMF model, he lives in a circle. The angles theta are periodic, okay? So I can compute on the circle the position of the center of mass. And when you do some simulations, you verify that your center of mass is moving, even though the total momentum is zero. So we have total momentum, the average velocity is zero, but your center of mass keeps moving. What's happening? Well, there's no contradiction, in fact, because here's a very simple example. Suppose I have a one-dimensional space, which is periodic. If one of the particles crosses one boundary, it shows up at the other boundary at the same speed. You can imagine that this is minus pi to plus pi, for instance, like for the HMF model. So I have one particle with velocity v, and the other one minus v, the average momentum, total momentum is zero, okay? This part, but the position of this particle is such that it crosses at the border before the other one, so he finds herself here. So we see, before the center of mass was here, now it is here. In fact, it moved, but it moved by a jump, okay? So it's, there's no contradictions. You can say it's an artifact of boundary condition. Yeah, but this artifact is real. It occurs in practice. I will show you a few examples. What causes this? The fact is, this is a distribution, this partial distribution for the, which you can compute exactly, for the HMF model as a function of theta here, and here minus pi to plus pi. And I just draw it with the maximum at zero. The first point here, which is very important, is that we have a degeneracy in the equilibrium position, because since we have a periodic space, the maximum of the distribution function can be anywhere. So it's a spontaneous symmetry breaking when your system becomes inhomogeneous. And this system has, in fact, a phase transition from a homogeneous to a non-homogeneous phase, what you can call a ferromagnetic to non-magnetic phase, also at a given energy. So in the case it is non-homogeneous, this is a typical distribution function. And if n is very large, or it goes to infinite, in the thermodynamic limit, the number of particles here is exactly the one here. But for finite n, we have fluctuations around this distribution function, okay? So the number of particles that, so I have particles that cross at each border, like in this figure here. But then that cross here, and a number of particles that cross at the other border. In the thermodynamic limit, the number of particles that crosses at each border is the same. But with finite n, it is not the same. There are some small, very small fluctuations, okay? So we can compute the number of particles that cross, for instance, at pi, plus pi here, which I call p plus, is given by this expression. So I integrate essentially all the particles that are a distance of the border smaller than p times delta t, then this is the number of particles that crosses at plus pi in a time delta t. Okay, is given exactly by this. The number of particles that crosses at the other border is the same one, because this is an thermodynamic limit, and okay, there's no motion over the center of mass, but it is given here. I can consider there are some very small fluctuations, and I can compute that in the following way. I say that the probability that k particles traverse at one of the borders, at plus or minus pi, is given by a Poisson distribution. P plus is a probability that one particle crosses. The probability that k particle crosses, you compose these probabilities. We suppose the crossing probability are independent. I neglect some possible correlations. And it's given by this expression, okay? Then all I have to, this probability that the k particles crosses in a time interval delta t is the same at the two borders, okay? But now I take the difference. What is the probability? That an excess of k particles traverse at theta plus pi than at minus pi. That means that I will take the probability that I have an excess of k particles traversing one side and the other. This will give the difference, a difference process between the two distributions. And this is the difference, the probability that I take two random processes described by a Poisson distribution, that the difference of the two variables is k, is given by what we call a Scalum distribution, not very known, but it exists, and is given, is very well known, and we have an expression, is just given by, it depends on one parameter, mu, which depends on the, which is given, I forgot, but it depends on the, each one of the, on the parameter, on the Poisson distribution, which is not here, but anyway, is given by, in terms of Bessel function with index k again. And in fact, no, that's okay. And we can compute in this way. So how the variance of the center of mass of this random process evolves in time. And if I do this computation, which essentially the variance is the position of the center of mass to the square, and I take an ensemble average using the probabilities of the system. We have this expression here, and the position theta is essentially, if we suppose that the initial position is a small number, I suppose it is given by integral of the momentum, and essentially this variance is given by this expression, and this average p0 pt prime is the autocorrelation of the momentum over time. This is how we compute diffusion in non-equilibrium systems. The autocorrelation we can compute this way, essentially the product of p at time 0 times p at time t. Okay, and I compute this autocorrelation p of t, solving simply the mean field equation, which is exact for this system, the thermodynamic limit. Theta, the derivative of theta is p, and the derivative of p is the force, which in this case is minus m sinus theta for a symmetric function, because in this case we don't have the magnetization have a well-defined orientation. And, well, in this way, we know also that the increments of the position of center of mass then will follow this scalar distribution, because it's just this excess of number of particles. What it will make? It will make the center of mass jump. For each particle in excess, it will jump a finite quantity, and then we have the scalar distribution, and we can compute this by a simulation also. And here we have the theoretical in black scalar distribution, and in blue the histograms for the jumps in the center of mass position here, which is exactly the same. It fits very well. Here is the autocorrelation of the position that we can use to compute the diffusion of the center of mass. Here is this function. And which is interesting is that it oscillates, but it goes to a steady value, at least for n very sufficiently big, which is different from 0. Which means that this is linear in t for a sufficient long time. Then we have this, since this is linear in t, this will result in a function of t. If it goes to a fixed constant value, the integral is proportional to t. So the variant, the standard deviation is proportional to t squared. This is ballistic diffusion. Okay, the center of mass begins with a ballistic diffusion, but due to collisions, this for a very long time can show that this autocorrelation function will tend to 0 very slowly. Then we will have a crossover from ballistic to normal diffusion of the center of mass. Here I show as an example from a simulation with 10,000 particles for a given this energy per particle. I show just the position of the center of mass. Here is the graph, complete graph. But if we do a zoom for a very small region like here, we see that the values are discrete because there are jumps. Each time one particle, an excess of one particle crosses at the border, your position of mass makes a jump, like in this figure here. You see, it jumps. So we have here, a finite number of jumps. And this is the evolution of this position of mass. And if you do the statistics, you will see that it is start as a ballistic diffusion and tends to normal diffusion. I will now show you a little movie for this HMF model from a simulation with 10,000 particles, just a little. Let me open. Here. Okay, so we have the time. In the horizontal axis is the position, the angle theta, and the vertical line is the momentum for each one of the 10,000 particles. The center of mass is here. If we look, it performs a motion. So your equilibrium, this is an equilibrium. In equilibrium state, the system, on the circle we have a structure, which is the equilibrium distribution structure, but it doesn't stay put. It moves on the circle, and this movement is a diffusive motion, as I explained it. And this is, in fact, the Goldstone mode. What is the Goldstone mode? I have a spontaneous symmetry breaking. That means my HMF model, it has a symmetry, rotational symmetry on the circle. But the equilibrium state spontaneously breaks this symmetry, and I can have an infinite number of different states given by the position of the center of mass that have the same energy. Then I can displace this structure without expending any energy. And the coupling of this mode, this Goldstone mode, to the thermal fluctuations in this due to a finite number of particles results in this motion of the center of mass with 0 average momentum. which is quite funny. How can something with zero velocity move? This is an example. Let me follow on. Where am I? Oops. Here. Achei, peraí. Oops. Voila. Here are some graphs. This is the magnetization, the two components, which is the average of the sinus and the cosinus. So if the center of mass moves, the average of the sinus of theta and cosinus of theta changes with time. But the modulus, mx squared plus my square root, is constant, which is given by the black line. Here shows you how these magnetizations move for very long times, you see? Because of this structure of the equilibrium state moving freely on the circle on a diffusive motion, okay? Here for, this is for, I think it's 10,000 particles, the same case. Here is 1 million particles. What happens is if I raise the number of particles, this diffusion becomes lower. And in fact, when n goes to infinity, this motion simply disappears because there's no excess of particles crossing. The fluctuations simply disappear. Okay. Another example I will give you now is for a 2D self-gravitating system. Okay, particles in a plane interacting by gravitational force. Let me again the same stuff here. You see, and then it breaks the symmetry. The equilibrium state, this is a non-equilibrium state. The equilibrium state for the system, it is symmetric. But here we have an example of a quasi-stationary state, which is not symmetric. And we can clearly see here a structure, a bar structure that rotates. Again, in a diffusive motion is the same idea. So one of the things I would like to see in the near future is to see what is in barred galaxies, if this phenomenon has some role to play or not, or is important or not. But here we can see this is a Goldstone mode where the periodic coordinate is simply the polar angle theta here. This is a two-dimensional model. In this case, we have in the vertical axis is the y component, in the horizontal axis the x component. The other movie for the HMF model, we had theta and p, but here is only space coordinates, and we can see this rotation. And the reasoning is exactly the same. I consider the angular position as an angular, and we have diffusion of particles in this direction that generates this motion of this bar. And if we run this simulation long enough, we start to see it here. It will slowly evolve to equilibrium, and it will become symmetric. Right done. We have here some what we call classical, there's no quantum here, Goldstone modes, which are excited by thermal fluctuations. It results from spontaneous symmetry breaking, as explained. There's a zero energy cost to go to one state to the other because states with different orientation or different position have exactly the same energy. So there's a zero expense of energy from taking one state to the other one. So there's what is called the Goldstone theorem that predicts the existence of these modes. Also applies to the classical domain. There are some works in this direction. So we see that periodic boundary condition thermal fluctuation excite the soft mode, causing a diffusive motion of the center of mass. And this is a characteristic of a long-range interaction systems, is that long-lasting memory that occur in those systems. They have a long-lasting memory of the initial condition, and this implies low decay of the velocity or momentum autocorrelation function, which implies super diffusion or a ballistic or almost ballistic diffusion that very slowly tends to a normal diffusion. This is very common in those systems, and we see this in the motion of the center of mass of the system. So we here we compute how much time do I have? Okay, so here I show essentially not do the is the variation with time of the variance of the position of the center of mass in the case of the HMF model with 5,000 particles and 500 realizations, and it follows almost ballistic motion here. The fit goes to 1.91, and then there is a crossover to almost normal diffusion with the fit in T to the power 1.09. So here we have this crossover from ballistic to normal diffusion after a very long time. This is only 5,000 particles at the time. Here's the order of 10 to 5. This crossover, it will occur for a much larger times when you increase n. It diverges with n, in fact. This phenomenon also occurs for. Here's the graph of this is essentially the inertia moment, let's say, in the case of the 2D gravitational model, which this inertia moment, the components of it oscillates and then it goes to a steady value where here we reach equilibrium. Just to finish now, there's also coupling of the motion of each particle on the HF model to this when the probability to exist function near the boundary is significantly different from zero. Then you have these excitations are possible. And if I look at the motion of a single particle in the mean field limit, which is essentially the equation of a pendulum, this pendulum will couple to the motion of the magnetization here. And this will, this coupling to this Goldstone model, we don't have time to go into details, but it will result here in transition in what we call from weak to strong chaos, which is measured here by the Lyapunov exponent of the system, of the motion of this pendulum. And here, for this energy is exactly, it's not a phase transition, but there is a soft transition when your Goldstone modes gets really excited. So you couple the motion of the particle to the motion of the Goldstone modes, which result in an enhancement of chaos and what we call a transition from weak to strong chaos, which we will discuss this in more details in the paper. I have much time in. So there are many things still to understand in this in applications of this. There's another application I did spoke here, which is in lasers. But this is also in the paper. Well, essentially, I have no more time. Thank you.
Unfortunately, we do not have time for questions. I hope you engage Tarcísio at the coffee break. Now we will have the talk from Professor Fernando Oliveira. And... Tá carregado? A gente pega um daquele ali. São dois? Ou ele carregou só aquele tempo ali? Sozinho? Ah, são dois. Os dois microfones mais abertos. Uma capela e esse teste.
Alô? Tá, agora tá funcionando. Teste.
Tá ok?
Aí eu e aqui no duplo até.
Ok, tá
Em
aqui o
cima faz
som.
laser.
Dá um laser
E aí vai
pra
mudar.
frente e pra trás.
Isso.
Ok?
O senhor tem vídeo ou só slide?
Só slide. Tem vídeo não? Ok. Okay. Thank you very much for the invitation. It's always a pleasure to be here, Mina. I know this institute in this center for a long time, since the beginning, since the 0 year. I'm going to talk about the fluctuation dissipation theorem and phase transition. And I'm going to talk about some things that most of you knows already, but with some different view, looking on different way to look for the problem. We are going to talk about phase transition, I mean, fractal dynamics. I talk very little about the growth dynamics and the phase transition. Well, the collaborators in this specific project are Henrique Alves, a student here, PhD student, Cauê, student as well, Edwin Mozo, which is in UF, I mean, the same group of Fabio, Ismael Carrasco, which is, I think maybe that's the reason why he's inviting me, because he's part of the work, so he invited me to talk about it. And Jairo Almeida from Universidade Federal de Pernambuco. Jairo Almeida is very new. He's going to collaborate more in the second part, which is disordered system. Jairo Almeida is the famous Almeida from Almeida-Taurus transition. Famous Almeida-Taurus transition. And the Professor Alex Hansen from Norway, Norwegian University of Science and Technology. Okay, let's start about talk about phase transition. I mean, what we are going to talk now is not about the Ising system. Ising is example to understand it better. We have, for example, the Ising systems at zero fielding, okay? Sigma, more or less one. Completely ordered. We have all the parameters, which is magnetization. I mean, you take it as the average of sum of spins. We know that closely to the transition, when temperature is T larger than T, well, I'm supposing here that D is larger than 1, because in 1 we have no transition. Suppose that D is larger than 1, 2, 3, 4, whatever. 0, field specific heat, we have some behavior like that. We have magnetization that goes like that. We have susceptibility, which goes like that. And we know for a very long time that those exponents are correlated. For example, that's famous relation obtained by scaling, right? Or statistical mechanics book, alpha plus 2 beta plus gamma to 2. And we know always that you have any exponents in any minus 2 equation. That's something well new for a long time. Okay? Some important things that you study are the fluctuations. I mean, here, for example, the fluctuation will be the spin at size I minus the average. But the fluctuation here is not only for spin. We could do it for example, charge density fluctuation, polarization fluctuations, density fluctuation in liquid, solid transition, and it could be any fluctuations. For a given fluctuation, we may associate with this a correlation function, which something like that. I mean, in LATS, it would be something like that, sum over the LATS. Well, it's well new as well that near a phase transition, we can do an analysis of that, consider the long wave long limit, and we get equation like that, which is, we consider that as mean field equation, which is nabla 2 plus kappa, which is a constant, applied to the correlation function, and you get the delta function here. And that equation here is easy to solve, is in this book, and the solution is just what is up part, A, 2 minus D, exponential de minus A, rho. Rho here is the correlation length, I forget to put here. That's inverse of kappa here. Rho is 1 of kappa, okay? Is the inverse of the correlation length, and obtained like that. But when you study statistical mechanics, a problem comes up. And what people do to solve the problem is like that. Suppose here that you are in a situation that R is much more small than rho. If R is much smaller than rho, the exponential goes to 1, and you have just a power law. It will be something like 2 minus D. But 2 minus D is not a good correlation function. For example, for D equal to 2, it will say that the correlation function does not change with R. It will be a constant. And that's something that cannot be, because if you have some spin correlates that increase the distance, you know that the correlation is going to decrease. That's physically. So that solution D minus 2 for R much smaller than rho does not work. And the feature 1964 proposed that to put some exponent eta here that we call feature exponent. It was a doc solution for the problem. He put it ad hoc, put it on the hand. It's very interesting article. So if you take an article from 1964, it's very interesting because it was done before renormalization group, all the scaling laws and everything else. People just adjust things and get things in. And Fisher got these solutions, I mean. And afterwards, people say, wow, that must be the solution, must be this eta here, and so on. And what people say is, we know that mean field is not good, we know that fluctuation relations obtained like that is not good. Okay, you go back to things here, everything goes as a power law, correlation length. This correlation length that appears like that, I mean, as t goes to infinite. So as t goes to tc, I mean, this correlation length goes to infinite, and you have the correlation function. That's what's happening close to the phase transition. Okay? Close to the phase transition, have a zero specific magnetic field, magnetization going like that, susceptibility going like that, and correlation length as well goes like that. And the correlation function is again like that. It's quite interesting to see that this eta is not an integer number. For example, here you have the dimension of the system, which is an integer number. 2, obviously, is integer, but the eta is not an integer number. Like all those exponents, we have one more exponent here, which is not integer. Okay, and in simple words, you would say that the eta here represents the violation of the fluctuation dissipation theorem. Okay, so I get to the point. Violation of the fluctuation dissipation theorem. It has a bad reputation because fluctuation dissipation theorem that fails many situations, just some. Well, I just talk about phase transition now, okay, where it fails. Spin glass, Edwards, Anderson, Sharon, Party, Paris, and so on, fails. Ballistic diffusion, we have some problem. Oh, by the way, all the first decade of the century, we decide our group here dedicated to studies of diffusion. Violation, fluctuation, dissipation theorem, anomalous diffusion, blah, 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 blah. So around 10 years, we have discussed that. And we have a lot of works on that. I mean, one of them is that one here. 2008, where we show a lot of the situation where it fails down and what fails down. The great advantage to study diffusion that we have done that time was that for diffusion, we could get a lot of exact results. I mean, you could get analytical results, exact results. So that's nice. I mean, you could understand what was going on. Well, those phenomena, KPZ, I mean, fluctuation dissipation violated. And we have discussed a lot, I mean, this kind of gross fluctuation dissipation theorem in the KPZ in the last few years. And what we want to do is how to recover the fluctuation dissipation theorem for phase transition and how to explain eta. Well, okay, let's go back now to the Ising system. Why Ising? Because Ising is something very, everyone knows how to do Ising, okay? So you take the 2D Ising model, zero field, and we started to look for the clusters that you have close to the transition, temperature very close to the transition, okay? And what you see is spin up, you put like white, spin down as black, and you see a lot of small cluster here. We have a small cluster here, big one, more big one, small, big, and so on. That lot is something like 3,000 by 3,000. I mean, so I have something like 10 millions of spins. If you do Salat, you see 5 times larger, 10 times larger, 100 times larger, whatever you do, we are going to see the same kind of stuff. Just to have bigger computer can go on, but the same kind of stuff. Correlation here, correlation system here, correlation here, correlation and so on. So it goes to, you get here clusters of all sizes. You don't have a specific size. We have what you call scale invariance. We don't have a specific row. So row goes to infinity, have all kind of scaling. And that's what we consider in phase transition. And that's what people study on renormalization theory. Okay, so let's see here. Okay. Let's go back to that. What you are going to do here is like that. You are supposing that the dynamics of the spin close to the transition due to the correlation between the clusters must be done on dimension, fractal dimension, df, which is smaller than the dimension d of the space. So that is the idea. So we are going to get all the equation. Remember that we have equation like that. The upper equation was like that. The former equation was like that. Minus number 2 square, plus and kappa here. Kappa is the inverse of this correlation length. So we are going to take this equation here on fractal space. So we are going to get things like that. Minus 2 here, that's Laplacian. But now to a power, which is a fractional power. And that gives you not a delta function in the integer space, but a delta function in the fractional space. And say, wow, it should be done in maybe 60 or 50 years ago or something like that. But it does happen that what you call Mandelbrot revolution, the fractal revolution, is an incomplete revolution. Because fractal dynamics is something that has been developing in the last 50 years. And just to have some ideas, I mean, the concept of fractal vector calculus is something that has been developed in the last 20 years. You have fractal derivative for maybe 50 years or more. But fractal vector calculus, like Gauss theorem and things like that, Laplacian and so on, has been something of last few years. For example, this guy here is a mathematician, Masolin. And in 2010, he showed that this Laplacian applied to a fractional derivative here, this fractional Laplacian, applied to this number here, will give you delta function, fractional delta function here. What's this constant? Forget this constant here, not important for us. So we have here a Laplacian with a fractional derivative, give you a delta function here with fractional dimension df. That's what we want. I mean, we want some Paul law here, some Laplacian applied to Paul law to get some fractional delta here. I mean, and when you do that, we get the correlation, and you compare with the previous result, you get relation between this fellow here and the what is and the what is in the correlation function. I mean, for this, if you apply that to that one here. So we get now a correlation that involves the eta parameter that we are looking for, the fractional derivative, df, and the zeta, the fractional dimension of the space, and the fractional derivative zeta here, around here. But still here you have one variable that you want, you have two different variables. And what we do is we use the Gauss theorem for a distribution of fractal. I'm not going to do that here. A lot of don't want to go over the calculations. So we use the fractional Gauss theorem, and we get that there is a relation between d minus df, which is exactly equal to 1 minus zeta. And we get that the feature exponent is exactly the difference between the integer dimension and the fractional dimension. Please pay attention. The lattice has an integer dimension, but the dynamics of the spin creates a fractional dimension, df. It's not the fractional, it's not a lattice, fractional lattice in integer space. It's an integer lattice, integer space, and a fractional df that arises due to the dynamics of the system. That's something new. And with that, we get, oops, again. And with that, we get that the Fisher exponent is this relation, which is identical to this relation. So there is some symmetry important here. The deviation that you have from the integer to the fractal dimension is the same deviation here that you have for one. I mean, one you have the normal Laplacian to this zeta here. I mean, the same kind of fractional things that we have here. Okay, now we need I mean, people don't believe you if you say something, just exact or some number. People want to see some simulations. And what we do is we take the 2D Eisen model, which is more simple. I mean, we know all the exponents. For the 2D Eisen, eta is 1/4. And we can get the df here, like 7/4. And we do some simulations. I mean, we have some method to obtain the fractal dimensions. And we have here the fractal dimensions in functions of the temperature. T equal to 1 is the transition temperature. That here is unity of transition temperature. So 1 will be exactly the transition temperature. And what we do here is to approach closely to the df. We approach this df dt plus this power law here. And adjust the curves, we get Yeah, for the F, we get something like TC, I mean, very close to 1, I mean, which is good indication that we are close to this situation. You can do it for many different values of the LATs, 1,000, 2,000, blah, 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 blah. And we get, that's the deviation of the temperature times 10 to 4. So you should put here -8 times 10 to -4. And here, -0.4, 6, -2, blah, 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 blah. Okay, here, for example, we have 4 with time 10 to -5 as well, the same point here. So what you see here is just fluctuation. I mean, we don't have even any kind of scaling, finite size scaling, and so on. I mean, even for 1,000, you get already good results. I mean, the numbers are just fluctuations around that. I mean, so we think that on the theoretical point of view and computational point of view, I mean, you get values which are visible on that. That is in this article here, I mean, that's archived 2000 now. And okay, we wanted to make a comparison now with that, with something that you get in growth phenomena. We have been studying growth phenomena for quite a long time, I mean, and the major idea on when you get the growth phenomenon is this. Well, you have a situation like that where it make the position here and so on. And what we do? First, you take the average height, which is that number here, on this system. And afterwards, you take your roughness, which is standard deviation of the height, which is something like that on here. And as you know, on mathematics, the fluctuation is error. I mean, the standard deviation is error. But in physics, the standard deviation, particularly in statistical mechanics, the standard deviation is a measure, something important. It's some response of the system. So we have a lot of properties of this standard deviation, but one of them that I wanted to call attention here is that when the time is very large, most of the system converges to a saturation value, which is proportional to the size L, again, another power law, to the exponent key here, okay? And for D larger or equal to 2, this is the same as we have obtained for the Fisher exponent. I mean, it's the deviation from the integer dimensions and to the part dimension. Okay, so let's go back again to the Fisher exponent here, which is this fellow here, d minus df. So for 2 dimensions, we know we have a Fisher exponent. So the fractal dimensions is identical, is some number, and you have big difference between the fractal dimensions and so on. When you go to 3 dimensions, it's decreasing. When you go to 4 dimension, where we have mean field theory works, eta is equal to 0. So for 4 dimensions, the fractal dimensions d is equal to df, and the eta equal to 0, and you go back to the former continuous mean field theory. Okay. The same happens for this roughness exponent. As we increase the dimension, this roughness exponent decreases and d gets close to df. But depending of the system, we don't have upper critical dimension. For example, this result here is very general, does not depend of the system. But if we have, for example, KPZ, we have that is, we don't have a finite, we don't have upper classical, we don't have an upper limit. Sorry, we don't have upper limit for the exponents. I mean, the exponent has no Okay, help. Let's say as a model, you have for 4 dimensions, you have the critical dimension. Sorry, the ICP system. Okay, for 2 dimensions, you have the exponent. 3 dimensions, you have different exponent. When you get to 4 dimensions, you have the critical dimensions, and that's it. Okay, so critical dimension for us here means that the fractal dimensions becomes identical to the dimension of the lattice. I mean, as we increase the dimension, the difference starts to decrease. Okay. We are studying now in how those things behave when you have a system which has a distribution like that, for example. You have an Ising model which is not uniform, but a disordered system. And we can see some result of that. We are not finished that. For example, the magnetization of the system is something that as you increase the disorder, the magnetization becomes less, and less. I mean, and we decrease the temperature, the transition temperature here, and the transition temperature becomes something like that on here. But still, I mean, we in that situation, it's complete disorder. We don't have more exact, simple result as we have before. And that's something that you're still working on that, and you expect to have good solutions for some time. Okay, conclusions are like that. I mean field works in proper fractal dimension. I mean, if you take the equations, previous equation uses proper fractal dimension, field works. I mean, in this situation, we recover the fluctuation dissipation theorem, and you give explanation for the Fish exponent, which is that one here. Fish exponent is the deviation between the integer dimension and the fractal dimension that are built in the lattice due to the dynamics of the system. So here, upper critical dimension means that eta equal to 0 and d equal to df, or df equal to d. We check it numerical for the Ising system with a very good precision, and notes that for d equal to large d1, that's identical to the roughness exponent, t, which is exactly the difference between d and the fractal dimension. That is not only a result for phase transition, but a connection between phase transition, which is something at equilibrium, and growth phenomena, which is out of equilibrium phenomena. Two things completely discorrelated, in principle. And we get this connection now here. Okay, that's it.
Professor Fernando's talk started 20 minutes later, which is not his fault, so we have plenty of time for questions. Although the time he expired, it was not his fault, so we have plenty of time for questions. Okay, so let's thank again Professor Fernando Oliveira. Now we go for the coffee break and the poster session.